Welcome to the Quantum to Cosmic YouTube channel with me, Ollie. Welcome back to this tutorial series on functions. This series is aimed at first year undergraduate university students or those who are just interested. Whether you just need a refresher on these topics or are learning them for the first time, you're in the right place. Today we're continuing with differentiation, looking at polynomial and series representation of curves. So if you're ready to learn, then let's get into it. In a previous video on stationary points and curve sketching, we looked at the local behaviour of functions near specific points, say zeros or stationary points, and the consequences of those for curve sketching. Instead, here we can consider a local approximation to a smooth function as a sequence of polynomials at a general point, x0 and f of x0. I'll draw this to give you some more clarity on what I mean. So as you can see, for our function f of x, we have these three increasingly accurate approximations for the point x0, f of x0, and I'll go through each one at a time. So the first one, the most basic one, is our purple line, and that represents just f of x being approximated as this constant line f of x0. And this would be known as the best constant. Obviously, best in the case of our point x0, f of x0. So next is our red line, which is our best linear line. And this is where f of x is being approximated as our constant line, plus this first derivative term times by x minus x0. So we basically just have this straight line. And it's sort of another way of writing our differential equation. So dy by dx equals the difference of y by difference of x at the point x0. And this is just the best linear approach. And you might see where this is going. Next would be our best quadratic. So each one of these is just adding another term to it to increase its accuracy towards the true f of x at our point x0, f of x0. We can continue in this fashion as long as there is successive derivatives at x0. So if derivatives of f of x exist at x0, then we can derive this Taylor series expansion at x0 of our function f of x. So the way we would write that is f of x equals f of x0, and notice here this is where our purple line would truncate. We can then add more terms, so f prime of x0 times x minus x0, and this is where our red line would truncate, and we can continue. So this is just showing the first few terms, x minus x0 squared over 2 factorial. Obviously these first two terms, that is divided by 1 factorial and 0 factorial here, but those are both 1, so it doesn't need to be written. So this is where our blue line would truncate, our quadratic approximation. And this can continue onwards until an nth term, so this would be f differentiated n times of x0 times by x minus x0 raised to the power of n, all divided by n factorial. And this can still continue onwards. It's an infinite series expansion of our function f of x. The validity of this approach, of this expansion to find the accuracy of approximation around a point of a function, will be considered more fully in a later video on this topic. But for now, let's look at an example of this Taylor expansion series. So if our f of x was sine x, and we wanted to expand this around the point x0 equaling 0, then we could write that sine x equals, well, f of x0, so sine of 0 is 0, plus x for f prime is going to be cos, and then cos of 0 is 1, and then you have x minus 0, so it'll be x minus 0, so that's x, plus 0 lots of x squared, because it will go back to minus sign for this term here. It's going to become minus sine x, and minus sine of x naught is going to be 0. Then you've got x minus naught squared divided by 2 factorial, so it would just be x squared. I mean, it would be naught divided by 2 factorial x squared, but it's naught, so we can ignore this term. So that's 0 and that's 0. And then continuing, our third term would be minus cos of x naught, and that's going to be minus 1. And then it will be x minus 0 cubed, so it will be x cubed over 3 factorial. So we've got minus x cubed over 3 factorial, and so on. And this, if you're at university at the moment, you'll be given several examples on your formula sheet for exams for the Taylor expansion of different functions, and I'm pretty sure sin x would be one of them. And we basically will result in this alternating pattern of positive and negative values, so it will be positive and negative, then a positive and negative, whatever, and it will be increasing in the odd powers of x, divided by their respective power factorial. So the next term would be plus x to the 5 over 5 factorial, then minus x to the 7 over 7 factorial, etc. And as an exercise, I'd like you to try and find what is f of x equaling cos x Taylor expanded around the point x naught equaling naught. And hopefully you can find how each term in the function relates to the next, so like we did here for the sin x. Just as a final remark about these Taylor expansions, these are local approximations about a point. So we have our point x naught. It might be better to alternatively seek a best polynomial approximation over an interval a,b. So we can do things like linear regression, find a best straight line and fit it to the data. For example, via the least squares method or any other type. It doesn't have to be a straight line either. But for now, we're not going to be considering that. And later on in this module, we'll be considering these expansions in more detail. Today, we've learnt about the polynomial and series representation of curves. This draws an end to the differentiation section of the functions topic. In the next section, we'll be looking at integration. So if you want to learn more, I'll see you there. If you learnt something new or just enjoyed this video, please hit the like button and don't forget to subscribe and tap the notification bell to stay updated on new videos. In the meantime, stay curious and I'll see you in the next one.